All right, everyone. I know we said I wanted to start a couple of minutes earlier this time because we lost a few minutes last time, but so let's just get going, please. Okay. I wanted to share with you this, and I want to see kind of what your thoughts are when you look at this picture. What do you think when you look at this picture? I do not have Instagram, but I've had this picture. I show it to my group every year. But what do you think when, and I thought I'd share it with you. It just occurred to me today. So what do you see when you see this picture? Pardon me? Okay. Okay. Hey, pardon me? Yes, okay, so let's build on that. So if he really wanted to, he could leave, but what's holding him up? Rich. Exactly, exactly. Sometimes the thing that is holding us back is our perception that we are tied up to something, and that thing could just be a chair, right? So I think it's a pretty powerful, very powerful image. All right. So we will continue with cooking our famous lobster or the eggplant or the zucchini. And last time we kind of went through the reasons for needing to do said cooking. And as engineers, you were tasked with finding the fastest way of cooking the lobster or the eggplant, whether boiling it in water, air frying it, or in oil, or baking it in the oven. And we did a bunch of assumptions. In the end, we got these two initial value ordinary differential equations that show you how the change in temperature. Let me pause this for a minute. Just quiet this. Okay. And so this is telling us what the time rate of change of the temperature of the lobster. So this T is the entire temperature of the temperature of the entire lobster. We assume that the temperature is uniform. There's no change between the tail and the head, for example, so that we get an ODE actually. Okay, and the temperature changes over time. So you put the lobster, it's at room temperature. You dip it in boiling water. How does the lobster heat up over time? On the left, this equation shows you what it would be, what the rate of change looks like if you're boiling it in a fluid. If you're heating it in a fluid, whether it be air, water, or oil, this is called convective heat transfer, and it highly depends on the temperature of the fluid, which is given by this T infinity. So the higher the temperature of the fluid, the faster you could potentially cook the lobster. But choosing different fluids has different implications, right? So water, for example, boils at 100 degrees at sea level. At my house in Sandy, boils at about 96 Celsius, right? But cooking in oil allows you to take that boiling point to like 280, 300 degrees, okay? So that's way higher than what water can afford. Now, why boiling is so particular? Once you hit the boiling point, the temperature of the fluid does not change, right? So that's the maximum temperature you can attain in the liquid, right? So that's why you would use a pressure cooker, because you could increase that boiling point, so effectively passing on more heat to whatever you're cooking, right? Because you're changing kind of the pressure of the fluid, okay? Now, all of these terms over here, we're just going to call them just like one coefficient, like capital H, once we implement this. And this coefficient has to do with how fast the fluid is capable of passing heat from itself to other things around it, right? I asked you the question last time, putting your hand in boiling water versus very warm air. You'd be like, yeah, probably very warm air is still gonna sting, right? But putting in boiling water, you're gonna probably instantly get a third-degree burn, okay? Because of this called advective or convective heat transfer coefficient. So for air, convective heat transfer coefficient is orders of magnitude. So by orders of magnitude, like factor, it's lower by a factor of 10 or 100, okay, compared to water, for example. Water and oil, they're about the same in terms of convective heat transfer coefficients, and it depends on the temperature you're at. But you have 2 degrees of freedom to play with here: the T infinity, or the boiling temperature of the fluid, okay, and the heat transfer coefficient. Whereas putting the lobster or the eggplant in a radiative heat transfer environment, you only really have control over this T infinity, which is the temperature, the radiating temperature. So that's when you set your oven to, for example, broil or bake at 350, etc. That's that temperature. But it has the tremendous effect of being raised to the power 4. Okay, so that tends to increase that potential gradient between moving, think of this as passing T infinity to the temperature of the lobster. Now, when this term is 0, there's no more change in temperature, right? Just like we saw in the example of the population growth. This coefficient here, we really can't do much. These are like constants for kind of black body radiation, etc. We're just going to take all of this as one coefficient, okay, over here. And the next step I described last time, if you remember, a kind of general strategy to solve this. We're going to get back to this once we look under the hood. But the first step we're going to do is we're going to use Python to solve this. And remember, we discussed this function, this routine in scipy.integrate called ODE int, which is similar to ODE int in MATLAB, if you've used that before. And it allows you to integrate a system of initial value ordinary differential equations. And it takes at least these three arguments. You need to at least have those 3 arguments. The etc. over here we'll discuss later when we want to pass arguments to the function. But at least it needs the 3 arguments: a right-hand side routine, which is just a Python routine to return the right-hand side of the ODE or system of ODEs you're solving. Okay, so this would effectively return either the right-hand side of the convective heat transfer equation, so H times T minus T infinity, or the radiative heat transfer equation, some coefficient times T to the 4 minus T infinity to the 4, okay? And phi 0 is just the initial condition. If you're solving a system of equations, it will be an array of initial conditions, 1 for each equation. And T is simply a linspace or an array of times. Okay, so you're starting from T0, T1, T2, T3. So that tends to define your time step size as well. Okay, so T1 minus T0 or T2 minus T1. Okay. Now, this right-hand side has a standard format. Always, 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 you define, when you're defining your right-hand side routine, it needs to take at least these 2 arguments. Phi, phi, which stands for the variable you're solving for. So in this case, temperature, okay? It just magically knows, right? It's going to call this right-hand side routine and give it the current value of the whatever you're solving for and the current time. And then inside this routine, you just use phi as if you know what it is to define your right-hand side. It's best to see this in action. So go ahead and download the lobster example with gaps from the ODEs module, or under your files, Jupyter notebooks. There's the lobster example with gaps, and we'll get to work through this together. Okay. Okay, so I'm gonna move this window over there. Okay, so this is what you should be seeing. Let me know if this is not what you're seeing. Okay, so it's got the entire description over here. We're not gonna worry about the description. I just described that. So initially, we're gonna import a bunch of boilerplate stuff, the usual, NumPy, Matplotlib, etc. And okay, so here I go ahead and I want to define, okay, the right-hand side for the convective heat transfer problem. Let me get you my slides so that you can put in the necessary numbers. Okay. Okay, so here I want to define, let's see if we can put them next to each other. Okay. So for RHS convection, what I need to define is minus HA over MCP times T minus T infinity. Okay, T is given to you over here. Time, we're not going to need it because the right-hand side is not a function of time. So time is not going to show up. So what you need to define here is all of these parameters that come into play, H, A, M, and CP. Okay? So, and they're given to you over here. You got M, you got CP, you got A, you got radius, you got length. So go ahead and define all of those. So for example, I would just start by declaring, H, which is the heat transfer coefficient. That's 500. So that's joules per meter squared per second. And then I'm going to define the length of the lobster, 0.3 meters. And the radius, which is 0.1, also in meter. Okay. Area. So not the area, the surface area. P dot pi times R times L plus 2 times pi times R times R. So that's in meter squared. Okay, mass is 1 kilogram. And the heat capacity, CP, is 4,200. So that's joules per kilogram per Kelvin. Okay. Now, we still need a T infinity, right? So let's start with T infinity at 374. So that's the boiling temperature of water. Okay. Now you go ahead and define your right-hand side. You assume that T is given to you, right? So in this routine, what do you have? You have T, okay? It's given to you. So you just punch in the right-hand side for the convective heat transfer ODE. You'll notice that in the way we've been setting up, and what's nice about Python itself and the way we've been setting up the problems is that we're trying to make the code look as much alike as the governing equation itself, right? Okay, so do the next one then, do the radiation one. Okay, if you're done with the convection one, go ahead and do the radiation, okay? Yes. Yes.
And like, what's it called? So in after the fact, so we're using like these values again. We're using some of them again. So would it be? So I process my information.
I know where you're headed.
Yeah.
We're gonna pass them as arguments later.
Oh, okay.
Because we're going to be changing them. We're going to be reusing them, right? We're going to be changing the value. It doesn't make sense to go back and edit this value. So, but that's going to be the next step, is to pass them as an argument to the function. But now let's just get kind of over this little bit. But great question. I suppose that was your question, right?
Yeah.
Yeah.
A lot nicer
No, because it's exactly what I'm thinking about. Like you just read my mind. Like when I'm solving, I'm like, why do I want to declare this H over here? It's just for us to get to a solution first. Okay. Thanks, Ryan. So if you're who's stuck at the convection? Are you done with the convection? Yeah. Okay. So let's see. What did we put? Simply a reflection of the governing equation minus H times A over mCp, okay, times T minus T infinity. Bam. Good. Okay. Let's do the radiation. We got the sigma, okay, equal 5.704 e to the minus 8. So that's what, or joule per meter squared Kelvin second, per Kelvin per second. And then epsilon, that's a dimensionless quantity, 1.0 mass is 1.0, so kilograms, okay. And then Cp is equal to 4,200. Okay, I'm not going to put the units anymore. L is 0.3. So just LRA. Just going to copy those from here. Okay. And then T infinity, I'm going to put it also at 500. Well, I'm going to put it not also. I'm going to put it at 500, assuming like that's like broiling level 1, right? Or whatever, 500 or 450. Okay. And then the right-hand side, simply minus sigma times epsilon times A over M Cp. We can kind of consolidate those together times T to the power 4 minus T infinity to the power 4. Okay. So what's happening here is that ODE int is going to be calling that's how you solve an ODE. ODE int solves y prime equal right-hand side. So to specify a unique ODE, all you need to specify is the right-hand side. The first time we're going to call ODE int, we're going to give it right-hand side convection. The second time, we're going to give it right-hand side radiation. Again, this T and time, it's an internal definition by ODE int. Says, okay, this is my right-hand side function. I'm going to call it back every time I'm doing an evaluation. We'll see why it has to call it back. I'm going to call it back. I'm going to give it my current value of the dependent variable. In this case, we're calling it T, and the current value of time to redefine, to recompute a new right-hand side value. Bring it back, integrate, and then repeat and repeat. Okay. All right. So now we don't need the slides anymore. All right, so here's what I got here. From some SciPy dot integrate import ODE int. Okay, now I need to declare my end time. Okay, and time is defined in seconds. Okay, in these, the units here that we're using are all in seconds, right? So I'm gonna run this ODE integration for 20 minutes. You can do it for 2 hours. Okay, but 20 minutes seems like probably like a reasonable time for a lobster to actually get cooked. So I'm going to run this calculation for 20 minutes. So I declare my end time as 20 minutes times 60 seconds per minute. So that gives me in seconds. Okay. And then time, you get a length space. I want to remember that. Let me pull up the slides again. The declaration for ODE int, it required this array time. Okay. So that's just simply this time array. I'm going to start from 0 to T end. Okay. My initial temperature, so I need an initial condition too. So that's phi 0 in ODE int. I'm going to assume the lobster is at 311 Kelvin, slightly maybe cooler than room temperature, potentially because it could be immersed in like water, for example. Okay, so now I'm ready to solve. So for the first one, I'm going to call ODE int for the convection case. I'm going to call ODE int, and I'm going to give it a bunch of things, and it's just immediately going to return the solution. So I'm going to store that in something called T convection. Same thing with T radiation. So let me show you the function call and go ahead and fill in the blanks. Okay, close the navigator. There you go. Okay. So go ahead and fill in the blanks. For T convection, you want to pass on the right-hand side for convection. For T radiation, you want to pass on the radiation right-hand side. Put it in and execute and see what happens. Oh, that was the giggle of victory. Oh. All right, so we're already getting some answers. So now go ahead and change, for example, the heat transfer coefficient, H, change T infinity and see what happens, okay? T0. T0. Right. Good. Now play around with the heat transfer coefficient, T infinity. Kevin, you've cooked a lot of lobsters in your life, so you know how this works. This doesn't work.
Yeah.
This doesn't look good.
Yeah, for some reason, whenever I run it on this computer, it doesn't show stuff. Like it's still there.
Yeah, it's kind of,
hard
yeah.
to see, but
Yeah.
I think I put something in wrong.
But
It
something
drops-
is
it
off.
drops from
Yeah, yeah.
2500.
Here, so look again at, you got a negative sign here. This is, yeah, so go up again. Yeah, so now try again, okay?
But my
You
baking,
guys?
my baking.
What?
Okay. Like 500 or something.
Yeah, let's see. Infinity. Okay, okay. You're getting some things. Cool, okay. Okay, baking and cooking. So what does it look like? Who's the winner? Which method is the winner? Are you all doing? Okay, you're changing heat transfer coefficient, etc. already. Good, Liz. See. Okay. Kara? Pardon me? Oh, you're still that stuff. Okay.
After I read the
It didn't run. Okay, so you need a, let me see. No, you can't, you don't give it the arguments here. You just give it the function name.
Okay.
All right, so it internally figures out what that function name is, right? So all you need to give it is right-hand side and then an initial condition and then the time array. So right-hand side convection, then the next argument should be the initial condition, right? So if you look at the signature, RHS phi 0T, right? Kimball, playing around your different liquids, okay? This is cool, huh? This is fun, yeah. It's actually in minutes. It should be in minutes. So I have a typo there. Yeah. It depends on H, right? So change H and change, yeah. You probably have a negative sign missing in the right-hand side for radiation. No, or convection. Is this, okay, what is this? Oh.
Is this 513?
Well, this is not going to work because you need either parentheses around it, right? Or just do e to the minus. Still off. Okay. So this is the baking. Let me see. L. 10 to the minus, it's 10 to the minus 8. That's sigma. Sigma 10 to the minus 8. Kimball?
What temperature is it considered cooked?
I don't. That's right. Right. So how? Yeah, that's a great question. Right. Right. Yeah. Yeah. So let's say, I don't know, 400. When is it okay? Who eats lobsters for a living? When is a lobster considered cooked? When is a lobster considered cooked? Like, let's say medium. I don't know if you want to eat shellfish medium rare. That's a good point, Kimball. Okay, but the illustration here is to show that how we can use this. So let's go ahead and take a look. So I had a typo here that Jake pointed out. So this time should be in minutes because I divided time by 60 over here. So for convection, I'm just passing RHS convection. I'm going to pass it T0, the initial condition, and the time array. Okay. Same thing for radiation, RHS radiation. Okay, and then I'm going to pass it T0, and then I'm going to pass it a time array. Okay, and then when I run this, okay, this is what we get with the parameters that we have obtained. Okay, so the blue line corresponds to boiling it in whatever fluid we chose, probably water, right? And you see it kind of reaches a point where it's not changing anymore. That's kind of the maximum temperature it's achieved, because after boiling, you're not changing anything. However, initially in radiation, so compared to the radiation, which is in orange, the boiling it or cooking it in the fluid achieves achieves a higher temperature much faster, right, in the first 5 minutes, but then radiation takes over, right? So Kimball asked the question, well, when do we consider the lobster cooked? Okay, like what temperature? Is it 400? If it's 400, then this condition, there's no way you're gonna be able to cook it in this fluid, okay, to achieve a temperature of 400. So how do we change this? We go and change our degrees of freedom, okay? And I want to drive a point here, going back to Ryan's point. Okay, so now to change, so Nile did something really cool. So she moved all of these outside these functions because they're kind of constant across all of these. So I'm going to do that here. Okay. And MCP, right? LRA. Okay. Okay, so how do you change this? You go back to your functions and you change your heat transfer coefficients. So let's say now we switched to oil. Okay, so our T infinity suddenly became, let's say, 674. I'm just making up numbers over here. Okay, and let's say your heat transfer coefficient stayed at 500. Okay, and the radiation environment, we kept it at 500. That's really kind of probably 550 is the maximum you can achieve in a oven at home. So now let's run again. Look at that. Just putting it in a different fluid is going to cook it like so quickly, which is kind of like really unrealistic over here. So probably our heat transfer coefficient was a little lower than this. Okay, so probably 10. Okay, now look at this. So the point is, this gives you a rational mechanism to scan different values of H, T infinities, okay, both for radiation and for cooking in a fluid, okay, to see which fluid you can choose. Because if you know H and T infinity for the fluid, you can say, okay, what is a fluid? Let's look at the encyclopedia of liquids. Can we create a liquid that is non-toxic, but that can allow us to, cook the lobster in a reasonable amount of time, for example? Okay, so that's kind of how you would approach this. It becomes like a PhD maybe. So now one thing to always look at is look at extremes. So what happens when H is very small? So let's say 0.01. Maybe we're looking at air frying, and then you go to what is it? My air fryer gets me to 450. Okay, maybe a 1. Okay, so look at that. When the heat transfer coefficient shrinks, you're kind of taking a long time to cook something. So my air fryer can cook frozen fries in about 25 minutes, 20 minutes, and it's like a hefty one on the air broil setting, which is 450. Okay, so it's different fluids, different conditions. You can play around with those and choose the right one. Okay. Okay. So now you notice how annoying it was every time we had to change h and t infinity, right? We had to go back to the right-hand side function, edit those, run, okay? Wouldn't it be cool if we could just change those like right over here? When we call T convection, when we call ODE int on convection or on radiation, excuse me, it would be really useful if there was a way to pass on any parameters, h, T infinity, area, mass, whatever. Pass them on directly to right-hand side convection or right-hand side radiation, so that we only need to change our parameters over here once, okay? In the final user interface, if you want. Turns out, yes, there is a way to do that. Let's switch back to the slides. Okay, so the next couple of slides show you the example, how you implement this, etc. A couple of results, okay? And the statement that you'll find, it's cumbersome to edit the right-hand side every time you want to change a parameter. Now, we could have used global variables like we did to declare the length and the mass, etc. of the lobster, but that's usually a bad idea. I do it in class because the problems are small in scope, and they're just to demonstrate something. But in reality, you should pass as much as you can as function arguments to allow for the most flexibility in manipulating parameters. So ODE int allows you to do that. So remember that, okay, those 3 dots in ODE int. So now imagine my right-hand side always has to start with phi and t, because that's what ODE int requires me. It requires that the first 2 arguments on the right-hand side are the dependent variable and the independent variable, okay? Phi and t, okay? Now, suppose your right-hand side depends on 3 other parameters or 50 other parameters like T infinity, H, mass, length, radius, whatever, okay? You go ahead and declare your right-hand side function as phi t, and then just append all the arguments that you need right next to it, so on your right-hand side. Then in ODE int, you still call your right-hand side function. You give it y0, you give it time, and then remember those 3 dots? There's an option called args equal a, b, c, or whatever extra arguments you need to pass to the right-hand side. So what this does, ODE int internally goes and calls RHS phi t, and it passes all of those arguments over here back to the right-hand side. So then you only need to change ABC like right above ODE int. Okay, so let's see how this works. Okay. Pardon me? Okay, so we go back here, passing parameters to the right-hand side. Now I'm going to keep L, R, and A, as non-parameters because, that's kind of the average lobster. I'm not changing the size of the lobster, but I want to be able to manipulate H and T infinity for radiation, for convection, and T infinity for radiation. So here's what I do. I take my convection right-hand side, called it right-hand side convection 1, for, because I'm not creative in finding other names. So convection 1, and then I just added 2 more arguments, H and T infinity. So now when the function calls right-hand side convection 1, it passes T and the dependent variable, independent variable, and passes the 2 other arguments that we're going to define later. As far as you're concerned, inside this right-hand side, T, time, H, and T infinity. So you just put them in here, okay? So see, H goes here, T infinity goes here. We didn't declare H or T infinity here. Same thing for radiation. What matters is the radiative temperature, T infinity, and that's going to be passed on as an argument. Okay. So now here's how we use this. So let's go ahead and execute these cells. And then again, create a linear space for time from 0 to T end. Initial temperature of the lobster, 311. So now here's what I'm doing. I'm declaring H, T infinity, and T infinity oven over here. So much easier to declare them here, manipulate them. And then we call ODE int, right-hand side convection 1, T0 time, args equal H and T infinity. Because those are the arguments that I declared for right-hand side convection. Anyone disagrees with this or like point of, contention? Pretty obvious. If we had needed another variable over here, let's say, CP, okay? So then there's no CP over here anymore, okay? But then you would declare a CP over here, your own CP, whatever. Oops. CP equal 4200, and you would pass it over here. That's all there is. Now, this is super useful because, again, you don't want to be changing things, changing the right-hand side every time you want to test a certain fluid, okay? So here I declare H T infinity oven. I call ODE int on convection, ODE int on radiation, and look for radiation. We're passing it the T infinity oven, okay? And that's it. Now, okay, let's run it. Now see how simpler this is going to be. Oh, look, we got this temperature profile. Let's go for, 4,000 heat transfer coefficient. Look at that. It cooked it like almost instantly, okay? Now let's go for a 10 heat transfer coefficient and do the temperature 600, the boiling temperature. Oh, look at that, right? So we didn't have to go back and forth and back and forth. This is the right way to do it, okay? You always pass things as arguments to functions, okay? All right. Okay, so now we are going to switch gears and go and discuss systems of ODEs. You see? Systems of ODEs. So just like right now we solved a single ordinary differential equation for the temperature, there are cases where you have 2, 3, 4, 1,000 quantities that are all related to each other. Like the simplest example that comes to mind are chemical kinetics, where you have reactants reacting with each other and producing products, and then products potentially reacting with the reactants, and so on, okay? So all of those are going to be dependent on each other, and you cannot solve one equation without solving the others. So you have to solve all of them concurrently. Thankfully, ODE int allows us to do that, okay? But I'm going to take this opportunity to also help you think about how you would design a system of ODEs for a very large class of problems. So the heat transfer problem that we saw kind of required some knowledge in physics and how heat transfer occurs when there's a fluid versus when there's radiation, okay? But in many other instances, ODE systems can just be set up by a simple balance of what's coming in and what's leaving the system, just like the population growth, okay? So I'm going to take this opportunity to teach you how to create systems of ODEs using what we call compartment models for ODEs. So this covers a very large class of problems in ODE modeling, okay? And we're going to use it to do a model for the pandemic together, okay? So now to drive the point home, I want you to consider a department store, okay? Macy's, Nordstrom, whatever you fancy, okay? And there's a bunch of people, shoppers, employees, solicitors, people inside the mall, okay? Inside that department store. So if you designate by n the total population inside the store, okay, so that's kind of like right now you went and looked at the store, there's like 2,223 people in there. That's the total population, okay, and inside the store. The store also has an exit and an entrance, okay? And people clearly go in, sometimes through the exit, sometimes through the end, like I do at Smith all the time, like, oh, exit, I'm gonna go through here, you know? And so, but people go in and leave the store at any instant in time. So the rate of change of the population n inside the store, so now we're thinking in terms of rates of change, right? So dn by dt is gonna depend on how many people are entering and how many people are leaving the store, okay? If people are leaving the store, then we expect the population n to decrease, and therefore we expect the rate of change to be negative, right? Obvious. So we declare this as dn by dt equal minus r out. R out is an absolute number, is a positive number of the number of people leaving, or the rate of the number of people that are leaving per second or per unit of time, whatever units of time you're using, okay? So if there's like, you know, 0.15 people leaving per second, then you have your rate of change of the population per second is minus 0.15, okay? Now, the larger the population in the store, like remember last time when we said the larger your population of paramecia or the lobsters, you know, the more that they're going to reproduce, right? So the larger the population in the store, the more people are likely to step outside. This means that the rate of depletion of people is also proportional to the population size itself, okay? So this can be written as dn by dt equal minus some parameter, okay, that you can measure and observe, times the population itself. You could have n squared over here, or you could have n cubed, okay? But the idea is this basic idea that the rate of change for people leaving is going to be a negative quantity. The same thing happens when people are coming in, right? If people are coming in, then the rate of change is going to be positive, okay? And we call that as Rn. It's a positive number, okay? And the more people that are outside the store, the more likely then they will come in, okay? And therefore, if you say that if the outside population is called I, or O, outside population, then dn by dt is beta I, or simply Rn, okay? Whatever that Rn is. So now that leads you to a simple, this is our compartment. There are things coming into the compartment described by Rn, and things leaving minus R out. That's the general formula for a compartment model for ODEs. You will find that this is what happens in chemical kinetics. If you think of each reaction or each reagent as a compartment, A going to B at a given rate, K1, for example, and then B going to C and D at a given K1 and K2. You can build entire ODEs just based on what's coming in minus what's leaving. That's it. Okay, so let's use this idea now to together develop a compartment model for epidemics. And we're gonna I promised you early on that we're gonna use this to analyze what we mean by flattening the curve, and kind of try to understand what that means. Okay, so in this model, we posit, you know, whoever came up with this model in the 50s, it's a very old model. It's called the SIR model. It's a model that consists of 3 compartments. A susceptible population. This is the free roaming population that is not infected, that is, you know, just moving around. Okay, they're all susceptible to be infected by a contagious disease. Okay, and then there's the population of the infected. This could be one person coming from out of state, for example, or like, you know, a couple of people that traveled into the general population. And then finally, you have the recovered population. Okay, so eventually the infected are going to become recovered. Okay, so this model does not account for hospitalization, for disease, etc. So it's a very simple model. Now, if you think about it, there's no way for the susceptible people but to eventually get infected. Okay, so there's only for the compartment of susceptibles, there's only one way out. Okay, like you can check out and you can check in anytime you want, but you can never leave. The other way around. Okay, so you can check out you can check out from the susceptible compartment to become infected. Now the rate, okay, so that model, that ODE for susceptibles, I need to step back. So these are 3 compartments here. We're going to have 1 ODE per compartment because all of those are going to be dependent on each other, and they need to stay in a certain balance. So we're going to describe that balance with ODEs. So for the susceptibles, they can only leave that compartment, okay, and they can only leave to become infected. Okay, so it's a one-way ticket. So that population of susceptibles, we call it S. The rate of change of the susceptible population is ds by dt equal minus R1 because it's being depleted. Okay, now we can think about R1. R1 is going to be dependent on the susceptible population itself. Okay, if you have 1,000 people on a room and 1 infected person, right, you're more likely to bump with the infected person versus if you have 2 people and 1 infected person, right? So again, we go back to the idea that the rate of depletion of the susceptibles is minus alpha, some coefficient that is a property of the virus. Okay, we will see that later, times the population itself. Okay, S, so minus alpha S. You're with me? Okay, so the rate of the susceptible population is decreasing, so we have a negative sign, and it's decreasing at a rate of alpha minus alpha S. But not only that, the susceptible people, might get infected from, breathing a virus in the air, but it's more likely that they're going to infected if they interact with an infected person. And by interact I mean being kind of within proximity in the same room, in the same hall, right? So it makes sense that this rate of depletion is actually the number of infected people times the susceptible population. So if you have 1 person, 1 infected person, so 1 I, and 1,000 S, that 1 I, effect of 1 I is going to amplify, right? But if you had 1 infected person and 2 susceptibles, there's less risk of of contaminating the entire population. So we see this beta times I times S. Okay, so it's the I times S is simply the mathematical description of an infected individual interacting with a susceptible individual, that product. Okay, so now we have the rate of depletion from the susceptible compartment, okay, described by minus beta IS. And you see this beta coefficient going from susceptible to infected. Now, beta is typically a property of the virus itself. It's essentially what they call the R0, the spread rate. It's different for flu, for a cold, for COVID, Omicron, Delta, right? It's different. So that number changes and you have to tune it based on observation. Okay. Okay, so now we come to the infected. As we said, the general compartment ODE is in minus out. Okay, so D infected by DT, the rate of change of the infected is equal to whatever is coming in. Oh, we're bringing in susceptibles. Let's infect them. Let's infect them. Minus the rate of what's leaving. Oh, they've recovered. We should be happy that they've recovered, actually. So now, what is coming in? The only thing that's coming in is coming from the susceptibles, right? So what's leaving susceptibles? But pardon me? No, well, exactly. What is the, Kimball? Yes, so it is the whatever is the amount, the rate of people leaving the susceptible compartment is exactly beta IS. And that amount of people, that rate, okay, of people leaving the susceptibles into the infected, they have no place to go but into the infected. So we have a beta IS over here. Notice that over there it's minus beta IS because it's leaving the susceptibles, and it's plus beta IS because it's coming into the infected, right? Follow the arrow. But we have also some people leaving the infected to become recovered. Okay. Now that once you're infected, you're infected. You have a fixed amount of time to be recovered. 2 weeks for COVID. 2 days with the flu. 3 weeks with a bad cold, right? So that rate is going to depend strictly on a property of the virus, which we're going to call gamma. Okay, so that's the amount of people leaving, the rate of change of infected that are leaving the infected compartment and becoming recovered. And that is going to be simply minus gamma I. It does not depend on any interaction between, if an infected person interacts with a recovered, they're not going to recover sooner. I wish it worked that way, unless I guess they get some plasma from them, but but an antibody cocktail, right? But it doesn't work that way in reality, right? So simply the number of people leaving, the rate of change of people leaving the infected compartment is minus gamma I. We still have one ODE. We need to close the system. So right now we have the following unknowns: S, I, and R. We have 2 equations, ds by dt and di by dt. We still need one equation, which is dr by dt. For dr by dt, there's only people coming in. Come people. Okay? And that is simply gamma I. It's those leaving the infected compartment and coming into the recovered compartment. For the infected, it's minus gamma I. For the recovered, it's simply gamma I. Okay? So that gives you a system of 3 equations with 3 unknowns, 3 ODEs with 3 unknowns, okay? And I modified the right-hand side here a little bit. I normalized the coefficients by the total number, by the total population, just to simplify a little bit the typing of the coefficients. But those are the ODEs that we just derived together, okay? Now, we're going to work on this together, but let me just kind of describe. This is one set of results with with some parameters for beta and gamma that I fixed and chose randomly. Okay, you start initially with, and this is the fraction of the population. 100% of the population is essentially, or 99.99% of the population is not infected. So that's shown in blue. Those are the susceptibles, and there's like one individual that's infected. Okay. And then they start interacting with each other, right? And as they interact with each other, more of the susceptible become infected in the red curve. And as the days pass, the infected become recovered, but also more of the susceptible are being consumed into infected, and more of the infected are being passed on to the recovered in green. And then you see a peak, right? And then, once you've reached this equilibrium point, okay, then the number of cases decrease. Your number of recovered and full immunity increases until you wipe out the entire population, okay? Well, wipe it, essentially pass through the entire population and have herd immunity. When we say we want to flatten the curve, it's this red curve that we want to flatten. Because that number, the peak of the curve in here, over here, is about 60%. This is saying like 60% of the population is going to get infected at one point. So if you have a population like in Utah, whatever, like 3 million, right? That's a lot of people. Okay, 60%. It's almost like 2 million people being in hospital beds. That's crazy. We can't handle that. So our objective is to flatten the curve, is to reduce that peak to be no more than our ER bed capacity, plus other diseases, right? Because there are people that need to be taken care of, etc. So that's what we mean by flatten the curve. Bless you. And so the problem with this model, what this is telling us is that we have no control over this, right? Because all of those beta and gamma are properties of the virus, right? So that's why, the idea of essentially lockdowns and kind of social distancing and all of that, and actually the masking tends to reduce beta, right? So if you have like a nice N95 mask, you tend to modify beta, the property of the virus, to get you infected, okay? And, with lockdowns, this model can't handle lockdowns, but, or social distancing. So we'll try to do that together after we solve this in Python. So let's go ahead and solve this system in Python, okay? Let me show you first how you would describe this in ODE int, okay? So you would simply write this as a vector of equations, just like we did dy by dt equals some right-hand side. Now you have the vector of si and r by dt is equal to a vector of right-hand sides, okay? The phi vector, okay, by dt is a right-hand side vector, okay? And in ODE int, okay, in ODE int, it solves that same system we just described. And phi is given by a vector of the first ODE, the second ODE, the third ODE, and all the way to the nth ODE. And your right-hand side is also a vector. So it could be a NumPy array or a list, okay? So that's I'm writing it here in this form that I like to write in Python as well. The right-hand side of the first ODE, the right-hand side of the second ODE, and so on. The only thing you need to make sure of is that the way you return your right-hand sides needs to be consistent with the ordering of the phis. So the first entry in your right-hand side function, return, needs to correspond to the right-hand side of phi 0, the first dependent variable. This will become clear when we type it, okay? Okay, so ODE int, you give it a vector of right-hand sides now, so it still looks the same. But instead of returning one in a scalar value, you're going to return a vector or an array of right-hand sides, starting with the right-hand side of the first ODE, the second ODE, the third ODE, and so on. Okay. Now, your initial condition is no longer a single initial condition. It's an array of initial conditions corresponding to the initial condition for the first ODE, for the second ODE, and so on. Time is still the same thing because time is shared by all of those ODEs. So it's simply like a lint space. Okay. So for example, for the right-hand side of the SIR epidemic model, I'm going to call it, declare a function, call it right-hand side, and I'm going to do the right-hand side 0 for ds by dt, right-hand side 1 for di by dt, and right-hand side 2 for the r by dt. And I'm going to return them simply as a list. Okay, as this vector of 3 values. Okay. For the initial condition, I have an initial condition on the susceptible, on the infected, and on the recovered. Okay. And finally, t is whatever, time from 0 to t end. Okay. So in the case of a single ODE, ODE int returned the solution of the only dependent variable, temperature in the previous case, at each point in time. So temperature at T0, temperature at T1, temperature at T2, it returned one vector or one array. In this case, it's going to return an array of arrays. Okay. The first ODE at all times going from T0 to T end. And in the second column, you're going to have the first ODE from T0 to T end and all the way to the last column. So what you will need to plot is you need to plot all of this for the first ODE. You need to plot all of this for the second ODE and so on. To access those, you simply do this. You use the semicolon. So you take the first, the 0th column, but you take all the rows. You take the first column, but you take all the rows for phi1, and so on. And that's how you plot it. Okay. And also, if the right-hand side has arguments, you do the same thing. So we discussed this earlier. let's go ahead and solve this problem together. So go ahead and download the system of equations, SIR epidemic model with gaps. Okay. Okay. Okay, how are we feeling about this so far? We haven't even gotten under the hood of what's going on. What I'm teaching you here is just how to be a technician, how to use the existing tools. We haven't even gotten into what's going on, those routines. But this is important because now you have a method to verify whatever code you're going to be writing to develop your own time integrators. Okay. Anyone feeling iffy on Zoom? You can still hear me? All doing good?
Can hear you?
Yes.
Oh, yeah.
Great. Thank you, guys. Okay. So if we have this SIR model with gaps, you just go through the boilerplate. This describes, okay, so let me fix this over here. ds by dt is, so this should be beta over n. Okay, so over here, I made a slight change. I simply divided beta by n to normalize the calculation. Okay, it's just a little technicality, and this is how I'm implementing it over here. Okay. Okay. So the first thing you want to do is define the right-hand side for your system of ODEs. I'm declaring a routine called RHS SIR, and it's taking an array of phi values. So for this problem, we should expect that phi has 3 values in it. The first value corresponds to the first ODE, S. The second value corresponds to the second ODE, and the third value corresponds to the third ODE. Okay, so phi should contain S, I, and R because that's the order I want to solve them in. And that order is really going to be determined by the order of the right-hand sides that you choose. So if I'm going to choose that the first entry is S, the second entry is I, the third entry is R, and my right-hand sides are going to be passed as right-hand side of S, right-hand side of I, right-hand side of R. Okay. So I first wrote the right-hand sides, and I wrote them as ds dt, di dt, dr dt, because that's actually the right-hand side, right? The right-hand side is ds dt, and the right-hand side for the second equation is di dt. So this would be the right-hand side for S, this is the right-hand side for I, and this is the right-hand side for R. And I simply wrote minus beta over n times S times I, and beta over n times S times I minus gamma I, okay? And same thing here, or equal to gamma I. So we still need S and I, right? Did I miss something? Nope. We still need S and I. So we're going to get that from phi. Remember, the right-hand side for convection and right-hand side for radiation, they had T in them. And that right-hand side declaration had T in the argument. So we just used that on the right-hand side. So this is exactly what we're going to do here. S is the first entry in phi, simply phi 0. I is phi 1, and R is phi 2. Now, we never use R over here, right? So there's no need for this, really, for this line. Now, what matters to get this order correct, what matters over here is to pass the right-hand, return the right-hand sides in the order you looked at phi. So the right-hand side, so phi 0 corresponds to this equation. We declared it as essentially we used S over here. So that means phi 0 is the first equation, and RHS 0 should be the right-hand side of the first equation. So I'm going to return here the ds by dt, and then I'm going to return di by dt, and then I'm going to return dr by dt. You can change the order, but make sure the meaning of these things is also changed. First equation, second equation, third equation, this should correspond to the right-hand side of the first equation, right-hand side of second, right-hand side of the third equation. And that's it. Okay. Well, that's not it entirely. I still have a question mark here. Okay. So we have S and I and R, but we have a beta. We have a bunch of parameters here that we haven't defined yet. And because I want to be able to manipulate those quantities, I want to be able to pass them around as arguments. I don't want to have to go and edit the right-hand side every time. So I want to pass a few arguments over here for the properties of the population and the virus. So I want to pass beta, n, and gamma, right? So you can just simply, in this question mark, here you just put in, we're going to pass beta, gamma, and n. You go ahead and execute this, okay? So now we go to solve this system. I'm going to start with a population of 3,000 people, okay? Initially, the number of infected is, I'm going to declare it to be 10 sick individuals. There's no one recovered initially. That's kind of my initial state. I'm kind of seeding the problem. And the initial number of susceptibles is the total population minus the number of infected initially. Okay? So total n minus I0. Okay? And start with a beta. Remember, beta, that's the rate, how infectious the virus is. Okay, that's where kind of masking and social distancing and whatever, you know, policies we want to try out, ventilation possibly, kind of changes. What changes? Beta. Gamma is your recovery rate. In general, it's equal to 1 over the number of days you need to recover. Okay. So for COVID, you could put 1 over 14. You know, for the flu, with a flu shot, maybe 1 over 2. Okay. Recover in a couple of days. Okay. And T end, I'm going to go for 100 days. Okay. That's what this is doing. Now, I declare my time array as going from 0 to T end. Okay. With a, I don't know, 1 day time step. Okay. So let's do 100. Okay. Over here. Initial conditions vector contains, in the right order of the equations, we're solving equation S first, equation I, and equation R. So you get S0, I0, and R0. And simply you call ODE int. Okay. So now for ODE int, it needs a right-hand side initial condition over here, time array, and the arguments. So go ahead and try to fill in this line. Similar to the right-hand side declaration we did before. Okay. Oh, great. Now change beta and gamma. Okay. See what happens. Make a very infectious disease or kind of very slightly infectious one. Ah. Yeah. Flatten the curve. Whoa, it's very infectious. Or essentially more interactions between infected and susceptible, right? Yeah. Yeah, let's just get everyone through, you know, herd immunity and just be done. Kara? Need help? Mhm. No, you need the semicolons. Yeah, and then comma. Yeah, yep. And then comma. Perfect. Yeah. Or plot. Michael. Oh. Now make beta smaller, make beta larger, change gamma, right? Yeah.
Oh, I got the widget going.
Oh, you got the widget? Oh, okay. That's cool, right?
Yeah.
Okay. Let's see. How we doing? Still kind of trying to understand. Pardon me?
Would argument somebody think it's beta gamma n or is it SIR?
What do you think?
If I remember correctly, how you're describing.
So-
it
so-
to-
RHS is already passed to ODE
it
int.
is?
So right, it's right
Okay.
here. So ODE int knows what your right-hand side function is.
Okay.
Now your right-hand side function is gonna need a few extra arguments, which are beta, gamma, and n, right? So you need to pass them through here,
Okay, so
right? Yep. And then the solution contains an array of arrays, right? The first column is S, the second column is I, and the third column is R. So to access that, you need to use the slicing. So sol, and then open bracket, and then the semicolon, and then, nope, you bracket, square brackets. Yep. And then the semicolon, then comma 0, and then comma 1, and then comma 2. You need a semicolon and then comma. Yep. Because it's an array of arrays. Okay. All right. So let's see. We are going to pass the right-hand side, SIR. Y0 is already defined. And your arguments are going to be beta. Okay. And then gamma. Right. And then n. Now remember, here, I declared my beta on purpose. I used a different nomenclature. I call it, / beta, right? So you need to pass beta here, this beta. You're passing this gamma and this n. Okay, and then you run it. Well, before you run it, solution contains, it's an array of arrays. Remember the slicing, sol 0, sol 1, then sol 2. And once you do this, you get that famous curve, okay? Some of you are already playing around with the numbers. So, for a less infectious disease, if we can manipulate beta somehow, you notice like it takes a long time for infections to happen and for the peak to happen. And we probably never reach a 20% of the population being infected at the peak, right, for this beta. So our objective really is to always modify this beta, okay? You can also change, so that beta, as I said, could be modified by increased, I don't know, lockdowns, masking, ventilation, all sorts of things, okay? And for the gamma, for the recovery, so let's say you remain infectious as long as you're sick. So here's a hypothesis. I hypothesize that the longer you are sick, the more infections you're going to cause, right? And the shorter your illness is, the less infected people there are going to be, right? So for a disease with a shorter illness span, it hits you and then you're recovered, I expect to see a smaller peak for holding all other conditions fixed, right? Do you agree with this hypothesis? I actually just coming up with that, so I hope that's my hypothesis, okay? And then the opposite is also true, that for a disease that takes a long time for you to get recovered, you're gonna still be infecting people, okay? So that peak is gonna increase. So let's go ahead and test this hypothesis. I'm gonna hold everything else constant, and I said that this beta is what controls this recovery rate, right? Because this beta goes from infected to recovered, okay? That beta goes from infected to recovered. So the larger the beta, right, the faster you are recovering. So let's do a beta of 1/2. Okay, beta 1/2. So I expect to see, look at that, it's just a very small, there's no bump, there's barely any bump. Okay, let's do beta 1/4. Okay. Beta 1/6. Okay, see? Now the bump, we're starting to have a larger bump. Beta, sorry, gamma, not beta. Gamma 1/40. Okay, that's a very small gamma. So it means you stay in the infected compartment for a long time before you get recovered. We're gonna see a huge bump over here. Look at that. Okay, good hypothesis testing. Okay. Okay. Now what I have at the bottom here is a little widget that you're welcome to kind of play around with, and this sort of you can do a semi-log process. This kind of where you can just kind of play around with these numbers. Simulation time, let's do like maybe 8 months, maybe. Okay. So you can change beta, you can change your gamma, recovery days. It's not changing, it's barely changing anything. Okay. Okay, there you go. Okay, anyway, so this you can kind of play around with this. Okay, I'm gonna put like oops. Just kind of get a more a cleaner one. Okay. Anyway, so this widget you can use to kind of play around with these recovery, et cetera, et cetera. All right, so let's take, actually, we're almost done. Let's not take any break. I just want to kind of discuss with you an opportunity to actually see. I have that slide on. Okay. So now go ahead and so now, okay, what if I want to take into consideration one second, I'm just gonna pick up those slides. So now what would you do? What would you do if you were to consider, we saw how this kind of beta, we want to change beta to control, to reduce the number of susceptible going to become infected. So one idea was, we do masking, etc. Another idea is social distancing, kind of. But how effective can social distancing be? Should you socially distance everyone 100%? Or could we get away with like distancing 25% or like 50% of the population? That's actually a question that my team asked early on in the pandemic. Like, well, there's clearly, a point of diminishing returns. Why don't we have like a reactive kind of distancing where, okay, we know we have 1,000 beds in Utah or 2,500 beds. Once we're reaching capacity, we increase our social distancing. And once, we are below capacity, we start reducing social distancing so that we can still have a life, but at the same time, we're not so overwhelmed, right? So there clearly is a bottom line there. So that's kind of somewhere in the middle between, opening everything up and closing everything down, right? And so if you were tasked with this question right now, using this technology of compartment models, right? And if you were to just simply add one compartment, okay, to this system to describe the socially distanced, what would you do? How would you do it? Just to describe social distancing. So to allow for susceptible people to either be socially distanced or not socially distanced, okay, like isolated or non-isolated. I would add one compartment, right? I would add one more compartment called distanced people, right? So let me show you. Okay, so I would add one more compartment called distanced. And susceptible people, can either be distant. So for example, the population that has, that are immunocompromised, elderly, for example, maybe that population could consider being more kind of under lockdown. Okay, so there's a group moving from susceptible to distance, delta 1, and then moving back from distance to susceptible because they're no longer locked down. And then the rest is similar, right? Infected and recovered. Now, do you think you can write the ODEs for this system? So you have S, I, R, but I added one more equation for distance. Okay, so think about this, okay? And do email me if you come up with a system of equations for that, okay? Because you'll get perks. Okay, Nathan, go ahead. No, we're assuming that the distance are under lockdown. The only way that for them to is for them to go back to susceptible, right? And then they become infected. I mean, you could go from distance to infected, but that's like going through susceptible and going to infected. So it tends to conserve that effect. Okay. If you come up with equations for this, okay, I will reward you. Okay, and you do email me. Okay. Another model, which you could add infected going to hospitalized and then recovered, then deceased. Okay. This model, you can measure these things. So it allows you to validate and verify and kind of fine tune the numbers a little bit better. So take this seriously. Think about developing the ODEs for these two and email me. Okay. Email me with a PDF kind of describing what you've done. I might reward you with something. Now, if all of you all right, thank you.
Thanks, Dr. Saad.